Okay, so if we move over to ARENA and the way it portrays the continuous probability distribution, you've got the probability distribution function and then finally the cumulative distribution function. If we take a look at the variables and functions that are associated with it, you can see that here. Again, the continuous function in ARENA returns a sample from a user-defined distribution. Pairs of cumulative probabilities, C sub j equals the cumulative probability for j, and associated values x sub j and the value of j are specified. So the sample return will be a real number between x sub 1 and x sub j, and will be less than or equal to each x sub j with corresponding cumulative probability C sub j. So the x sub j's must increase with j, the C sub j's must all be between 0 and 1, and must increase with j, and C sub n must also be 1. Okay, let me just zoom in for a bit here. Or zoom out rather. So the cumulative distribution function, f sub x, is piecewise linear with corners defined by f sub xj equals C sub j for j equals 1, 2, up to n. Thus, for j greater than or equal to 2, the return value will be in the interval of x sub j minus 1, x sub j with a probability of C sub j minus C sub j minus 1. Given that in this interval it will be distributed uniformly over it. So when utilizing this, you need to be careful to specify that C sub j and x sub j to get the effect you want at the left edge of your distribution, because the continuous function will return exactly the value x sub j with the probability of C sub j. So if C sub j is greater than 0, this actually results in a mixed discrete continuous distribution returning exactly x sub j with probability C sub j and with probability 1 minus C sub j. A continuous random variate on the x sub j, x sub n as described up above. So the graph f sub x would depict the situation where C sub j is greater than 0. On the other hand, if you specify C sub j equals 0, you get a truly continuous distribution as described above with no massive probability at x sub j. In this case, the graph would be continuous with no jump at x sub j. As an example use of the continuous function, if you had a set of data that you had collected, x1, x2, and so on up to x sub n, assuming it's assumed to be sorted in increasing order on service times, for example, rather than using a fitted theoretical distribution from the input analyzer, you might want to generate service times in the simulation directly from the data. Again, if I've got data on the system, I want to utilize that, and this will be consistent with how they're spread out and bunched up and between the min and the max you observe. So assuming you don't want a massive probability sitting directly on x sub j, you'd specify C sub j and then C sub j equals j minus 1 divided by n minus 1 for j equals 2, 3, and so on up to n. So your range is established by that as well, x sub j up to x sub 1, and the continuous empirical distribution, again, is often used to incorporate actual data. So I got actual data on my physical model from some sense, possibly something like a fast food restaurant. Maybe I'm contemplating changing the way I take orders and have customers pay for those orders. So I don't maybe know what that's all going to look like, but I do know what my profile of customers coming in the door is. So I may take that and utilize that directly into the model because it by nature is likely to be better than a distribution I might pick. So that's a useful thing to do with this particular distribution. So again, this distribution can be used as an alternative to a theoretical distribution that's been fitted to the data, such as in the data that have a multimodal profile or where there are significant outliers, okay, which is not unlikely with real data, okay? And we'll talk about that more. The closer that we can understand our outliers and how it interacts with the mean of the data set, to some extent the easier it is to manage statistically in terms of using things like normal distributions where they're easy to specify. In the case of normal distribution with only the mean and the standard deviation being my only two characteristics that I need to worry about. So But we'll get into that in a little bit here. So, okay, so discrete uniform distribution, pretty much the simplest of the discrete distributions, and applies when all the outcomes have an equal probability of occurring. So a nice sort of squared off distribution curve. Figure below represents a uniform discrete distribution. 5 possible outcomes, each occurring 20% of the time. And you can see those here, these 5 data points. So the discrete uniform distribution, again, is best reserved for circumstances where there are multiple possible outcomes, but no information, which is what's being shown here, but no information that would allow us to expect that one outcome is more likely than any of the others. Okay, so I've got, to some extent, not a whole lot of data. Understanding the richness of the data is not maybe as good as it needs to be. So maybe I use this early on because I don't know much about it. So I'm going to assume that I have these 5 outcomes or these 10 outcomes, whatever it might be. And I'm going to assume that the probability of if any of those occurring is equal to each other. So that would be where you might use something like this. With continuous data, you cannot specify all possible outcomes since they're too numerous to list, but we do have a couple choices. First, we can convert the continuous data into a discrete form, which is what we're doing in our simulations and discrete event simulation, and then go through the same process that we went through for discrete distributions of estimating probabilities. So for example, we could take a variable such as market share and break it down into discrete blocks. And we could say we're interested in market share. And market share is a term used for companies that are selling a product. How much of the market do they possess? If you're Apple selling cell phones, and there's 1 million phones sold in a year, just to pick a number, and you sold 300,000, that means you have a 30% market share. So that's what that term means, and we'll have other terms like that that'll come up. Again, these are areas where statistical analysis is looked at quite a lot. So maybe we break it down into discrete blocks, say a market share between 3 and 3.5, between 3.5 and 4, and so on. And then we consider the likelihood that we'll fall into each of those, into one of those blocks. The second method would be to find a continuous distribution that best fits the data and specify the parameters of that distribution. In our case, using our software, we would probably fall into the first category and take that data and bust it up into blocks, and then look at it in that in that sense. And that's a pretty common thing to do. So on the again on the ARENA side, this is how it's specified: discrete, cumulative probability, value, cumulative probability, value, and so on, and then individual probabilities as well. So here's your 2 functions, your probability mass function, and then finally your cumulative distribution function. So the discrete function in ARENA returns a sample from a user-defined discrete probability distribution. That distribution is defined by the set of n possible discrete values. That's noted by x1, x2, so on up to xn, x sub n, and that can be returned by the function and the cumulative distributions denoted by c sub 1, c sub 2, up to c sub n, associated with these discrete values. So the cumulative probability c sub j for x sub j is defined as the probability of attaining a value that's less than or equal to x sub j. So again, looking at it from a cumulative standpoint, I think the graphs up here sort of illustrate that pretty well. So again, hence c sub j is equal to the sum of p sub xj for k going through from 1 to j by definition. And the cumulative probability, again, for c sub n would be 1. Okay, so 0 to 1 would be the sort of the range there. So again, the applications of this, discrete empirical distribution is often used to incorporate discrete empirical data, again, directly into the model. So this is a good method, as I mentioned earlier, to take data that I've got. I talked about like arrival times at a restaurant. Maybe I've got that pretty well understood. What I don't have a good understanding of is the processing that takes place and how I tweak that and how that affects the outcome. So if I've got good data, again, I want to try to utilize that. If I can use it directly, that's great, or at least use it to test the distribution that I picked, and we'll talk about that in a bit as well. So again, this distribution is frequently used for discrete assignments such as job type, visitation sequence, or batch size for an arriving entity. And again, I've got the data, utilize it. Okay. Okay, so the Erlang distribution is unique in that it involves multiple independent variables. And what it entails is a series of independent variables, x sub 1, x sub 2, up to x sub k. Independent variables, again, so there's no interdependency between them. They're identically distributed exponential random variables, so it's all exponential distributions. So if I have that condition, then the sum of these k samples, again, x sub 1, x sub 2, up to x sub k, has an Erlang k distribution. The mean of each of the component exponential distributions and the number of exponential random variables are the parameters of the distribution. And that's what's shown up above. And that's how it's specified in the ARENA simulation, is with these variables here. So the exponential mean is specified as a positive real number, and k is specified as a positive integer, and that's by nature of the exponential distribution. My range on this would be 0 to positive infinity. My mean would be k times beta. Beta defined here as the mean. K as the number of variables, or independent variables. Variance, k times beta to the second power. Okay, again, beta being the mean, k being the number of random variables. And the points there that are important, the key words here are independent and random, and of course that they're exponential distributions. So the Erlang distribution, again, it's used in situations in which an activity occurs in successive phases, and each phase has an exponential distribution. For large values of k, the Erlang approaches the normal distribution. So large values of variables, the Erlang would approach a normal distribution. And the Erlang distribution is often used to represent the time required to complete a task. So it's a special case of the gamma distribution in which the shape alpha is an integer k. And the gamma distribution we'll talk about, that's one of the distributions we'll talk about here in a bit. Okay, so next on our list is our exponential distribution, and this is one I'm sure everybody's pretty familiar with, pretty characteristic shape to it. If we move into the ARENA world, our probability density function, shown here by this graph. The mean beta is specified by a positive real number. Again, just like the Erlang, shown up above here, our range would be 0 to positive infinity. Mean would be beta. In this case, there is no k because there is only one variable that we're looking at, so our variance would be beta to the second power. Distribution is useful to model inter-event times in random arrival, so maybe between events, travel times, things like that, and breakdown processes. But generally inappropriate for modeling process delay times. And we'll get into that as we get into using this in our ARENA simulations. So in ARENA's create module, the schedule option, which is something that we're jumping ahead a little bit, but something we'll use where you're using time-based arrivals, and you're specifying those arrivals and the time duration between the arrivals. The schedule option automatically samples from an exponential distribution with a mean that changes according to the defined schedule. Okay, so you define that mean. I'm not sure if we went over that at all last time. I think I showed the schedule real quick where you establish the values. It's a graphical entry system, very easy to use, very easy to change. And that's what you're really changing. And then the distribution of those samples within that schedule is based on sort of an embedded exponential function that they use. So service applications, retail businesses, call centers, where the volume of customer changes through the day. Again, to back up for a second, using this with the schedule option, only in that time slice. You'd specify the mean within a time slice, and then the actual discrete event slices would come from the exponential data set that the software determines. But you can actually change that mean based on the time. So if we go back to an example, I think we talked about last time, if we're talking about a fast food restaurant, Certainly at breakfast time between 7 and 9, the volume of customers would be higher than probably between 9 and 11, where it would pick up again for the lunch crew. So that is something you would specify the mean for whatever time slice you want. Now in Arena, you can do that as well by half hour, by quarter hour, even down to the I think you're limited to 1 minute, but pretty fine resolution on that. Okay, the next distribution we'll talk about a little bit is gamma, which again we talked about a little bit up with Erlong, right? Erlong is a special case of the gamma distribution. The parameters that you look at for this in Arena, and again this is how it's specified in the Arena nomenclature, gamma and then parentheses beta and alpha, beta being the scale parameter and alpha being a shape parameter, okay? So you can see some examples of that here. Equations that drive it over on the right. The mean on this again would be simply alpha times beta. Variance would be alpha times beta squared, much like the Erlong up above here that we talked about previously. Okay, so applications, integer shape parameters. Our 4 integer shape parameters, the gamma is the same as the Erlong distribution. The gamma is often used to represent the time required to complete some task. Examples of that, machining or machining repair time. So we will utilize this in our in some of our simulations. Again, that's gamma, similar to Erlong, Erlong being a subset of gamma. Okay, next is the Johnson probability density function. You see some examples of it here. Has some similarities to a normal curve. The specifications for this, again, there's a shape parameter, shape parameter gamma, the delta shape parameter, and the lambda scale parameter. And finally, the location parameter, x sub I. So the range on this, there's 2 different ways this distribution can be used as an unbounded or bounded family. For the unbounded, the range is negative infinity to a positive infinity. And then for the bounded condition, you've got your xi location parameter and your lambda being used as your range, or actually your xi location at one end, and then your xi I location plus your lambda scale parameter at the other end of your range for the bounded condition. So again, a very flexible distribution, and you can see that from the range of curves that you can see up above. Again, you can use in Arena either the unbounded or bounded form. Delta is passed, if delta is passed as a positive number, the bounded form is used. If delta is passed as a negative number, the unbounded form would be used, which you can see up above here. Okay, so that's the Johnson distribution. I haven't used that one in Arena as of yet. Not sure if we'll see an application where that might be a fit. So that one's a little bit less familiar than some of the others. Okay, so in the real world, most data does not exhibit tremendous amounts of symmetry. We like data to exhibit symmetry, and we like to use symmetrical distributions because it simplifies the math significantly. And that's part of the reason that the normal distribution, which we'll get into here in a bit, is so widely used. And we tend to try to utilize that wherever we can because it gives us sort of ease of calculation, ease of understanding. 2 variables, basically, in the case of the normal distribution, the standard deviation and the mean, allow us to fully characterize that population distribution. So it's very useful. But in reality, that symmetry is not many times exhibited in the physical world, and instead it'll skew, and we measure that, and we'll talk about skew in a little bit when we talk about data characterization. But it skews towards either very large positive or very large negative numbers. So if the data is positively skewed, one of the choices we can use for a distribution is a log normal distribution. And it's typically characterized by, again, 3 parameters, sigma, shape, scale, which is mu and a shift parameter omega. So when mu is 0 and omega is 1, you have the standard log normal distribution, and when omega is 0, then the distribution requires only scale and sigma parameters. And as the sigma rises, the peak of the distribution shifts to the left and its skewness in the distribution increases. And the figure that I've shown below here sort of gives us some examples for various, and let me zoom in on that just a bit. It gives us some representative curves for various values of the variables, in this case sigma, that's driving it. So useful distribution again for data which tends to skew towards either very large or very large positive or very large negative numbers, which many times is something that you'll see in terms of ARENA. What it's looking for is mu and sigma, and log normal, log mean, or log standard is the log mean and log standard are the two variables it's looking for. Okay, so you've got the equations that drive this here. You've got a probability density function shown here, and you can see that that's skewed, not like not characteristic normal curve, but skewed in one direction. So again, the mean, log mean, and the standard deviation, log standard, are of the log normal random variable. They both must be specified as positive numbers. Our range in this case, again, 0 to positive infinity. You can see the mean calculated here and the variance calculated here. So again, the log normal distribution is used in situations in which the quantity is the product of a large number of random quantities. So task times that have a distribution skewed to the right, this distribution is related to the normal distribution as follows. If x has a log normal distribution, then log of x has a normal distribution. So note that mu and sigma are not the mean and standard deviation of the log normal random x, but rather the mean and standard deviation of the normal random variable log of x. Okay, so that's the log normal distribution. Again, wide range, flexible because a wide range of conditions can be simulated with this, or portrayed with this, I should say. Okay, finally the normal distribution. This is, again, one of the more popular. And we'll talk a little bit about statistical process control and how that relates to manufacturing, and to some extent how it would relate to simulation. Normal distribution is used extensively in that area. And really, as I mentioned before, a couple of reasons. I can characterize it, which is two parameters, the mean and the standard deviation. So it's less painful to utilize. And the probability of any value occurring can be obtained simply by knowing how many standard deviations separate the value from the mean. So the probability that the value will fall 2 standard deviations from the mean, roughly 95%. So that's a useful property in that I can characterize that distribution pretty easily, and the math to get there is pretty straightforward. So again, the normal distribution best suited for data that at a minimum meets the following conditions. A very strong tendency for the data to take on a central value, and you can see that clearly from these curves. The curves are all different, but you can see they're all symmetric about some mean, okay? And the second point, that the positive and negative deviations from the central value are equally likely. In other words, if I'm looking at this orange curve, the possibility of being over here on the positive side are equally likely to being over here on the negative side. Same thing if I look at this green curve, likelihood of being here, same as likelihood of being here. Okay, so that's an important concept. And that the frequency of the deviations falls off rapidly as we move further away from the central value. And you can see that in varying degrees with these curves. If you look at the orange, the frequency drops pretty dramatically as we get away from that central value. So that central value up here at 0.9, you know, I'm one unit away basically, and I'm down to about 0.1. So that's a pretty rapid drop in a pretty short, pretty steep slope on those curves. So the last two conditions show up when we compute the parameters of the normal distribution. The symmetry of deviations leads to zero skewness. We talked about skewness being asymmetrical. You can see the normal distribution is symmetrical. So that zero skewness is driven by our symmetry of deviations. And the low probabilities of large deviations from the central value reveal themselves in no kurtosis. And we'll talk about kurtosis, but that's basically got to do with the shape of the curve, the flatness of the curve. But there's a cost that we pay, though, when we use the normal distribution to characterize data that's non-normal, because the probability estimates we obtain can be very misleading and can do more harm than good. So depending on if you're using this normal distribution and your data sets do not really correspond well to that, you can wind up with some results that are less than accurate. So when the data is, for example, when the data is asymmetric, another potential problem is a problem. And another potential problem is when the probabilities of large deviations from the central value do not drop off as precipitously as required by the normal distribution. So in statistical language, the actual distribution of the data has fatter tails than normal. But when all the symmetric distributions in the family are like the normal in terms of the upside mirroring the downside, they vary in terms of shape, with some distributions having fatter tails than the normal and others more accentuated peaks. So there's a couple other distributions that are out there, such as the Cauchy distribution, which is used but isn't supported by ARENA, which basically are normal in shape, roughly, but they're fatter. They're not quite as precipitous a drop, if I go back up here, as you see here from that mean value. It's more of a less of a severe drop than you see there. So if we go to ARENA nomenclature again, the mean, mu, and standard deviation, sigma, are shown here, and that's really all you need to specify, or to characterize, I should say, a normal distribution. Range is negative infinity to positive infinity. Again, the mean is mu, variance is sigma squared, which is our standard deviation squared. And you can see the formula that drives that over here on the right. So again, the normal distribution is used in situations where the central limit theorem applies, and that is that the quantities that are sums of other quantities. It is also used empirically for many processes that appear to have a symmetric distribution. Because the theoretical range is from negative infinity to positive infinity, the distribution should only be used for positive quantities like processing time. And again, it's utilized a lot because, again, the math behind it and the statistical methods that we use are pretty straightforward, significantly simpler than some of the other distributions that we look at. So if our population can fit this reasonably well, this would be something that we would probably certainly try to use. Okay, so another distribution is the Poisson distribution. And this distribution measures the likelihood of a number of events occurring within a given time interval. So the key parameter that's required is the average number of events in the given interval, I. The resulting distribution looks similar to a binomial distribution, with the skewness being positive but decreasing with interval. Okay, so the figure below represents 3 Poisson distributions. In this case, the range on these 3 varies, as you can see here, from 1 to 10. So 1 being the red, green being the 4, and finally the black one being 10. In terms of ARENA, the Poisson requires the mean. You can see a graph of the probability, or histogram of the probability mass function here. And the mean lambda is specified as a positive real number. Our range is our natural counting numbers, mean and variance being the same at lambda. So Poisson is a discrete distribution that's often used to model the number of random events occurring in a fixed interval of time. So if the time between successive events is exponentially distributed, then the number of events that occur in a fixed time interval has a Poisson distribution. And the Poisson distribution is also useful in modeling random batch sizes. Okay, so that again would be probably a service type organization. Typically that's not a manufacturing situation where you've got random batch sizes. So again, useful for arrival times type thing, where you've got random events. You really don't know the quantities, but they're fixed interval time you have set in your simulation. So another distribution that we use, very straightforward one. It's got bounds to it, so it's sometimes useful for some of the stuff that we do. And it's used where there are natural limits on the values of the data that the data can take on. So as we discussed earlier, the revenues and the market value of a firm can't be negative, and the profit margin can't exceed 100%. So we've got some natural limits on that data set. And if we use a distribution that does not constrain the values to these limits, we can obviously wind up with some problems. If we use, for example, a normal distribution, again, because it's straightforward to use, and we're describing profit margins, if we end up with profit margins over 100%, then we've sort of violated the model, right? Or the reality that would be possible with the model. So when data is constrained, the questions that needs to be answered are whether the constraints apply on one side of the distribution or both, and if so, what the limits on the values are. Once you've answered those three questions, there's two choices. The first would be to find a continuous distribution that conforms to the constraints. And an example might be the log normal distribution. Could be used to model the data, such as revenues and stock prices, that are constrained to be never less than 0. And for data that have upper and lower limits, you could use the uniform distribution. If the probabilities of the outcomes, however, are even across outcomes, or a triangular distribution would represent another, if the data is clustered around a central value, would be a useful tool. And you can see that here, very straightforward. If we pop down here to the arena, what it's asking for a min, which is a value here. It's asking for the mode, and then finally the max. So useful tool to model. Very straightforward, very easy to use. And you can sort of pick these values. We use this for a number of different things in areas where we could come up with a reasonable idea. So it's used again in situations where the exact form of the distribution is not necessarily known, but estimates for the min, max, and most likely are available. And the triangular distribution is easy to use and explain than some of the other distributions that we've looked at, like the beta and others. So it's fairly simple. We used it for things like arrival times, processing times. You know, if we're looking at a processing time, say we've got a manufacturing operation, drilling a hole in a part or whatever, most likely it's going to take, let's just say, 2 minutes to do it. But we know it once in a while, maybe it takes 1.5 minutes, but it really never takes longer than 3 minutes. So we can set that up real easily, easy to understand, sort of intuitive. One of the things we want to do with any of our simulations is to be able to tweak them and then understand how robust the simulation might be. And that's easy if you have a really good understanding of the impact of changing variables is going to have. And this is really intuitive from that standpoint. Much easier to understand than some of the others, which can be a little tricky. Okay, so next distribution we're going to talk about is a uniform distribution. And this is sort of the extreme of the case where the extreme values increase relative to the central value. And this, in fact, is the limit of that. So the distribution flattens out. So at its limit, we're assuming the data stays symmetric, and we put limits on the extreme values. We end up with a uniform distribution, as you can see here. So basically, all values are the same level, or at the same level for this. When would it be appropriate to assume a uniform distribution for a given variable? One possible scenario is when you have a measure of the highest and lowest values that a data item can take, but no real information about where within the range they may fall. So in other words, any value is within that range is just as likely as any other value. And again, there's the distribution from using the arena format. Min-max are what we plug in for the uniform distribution. And again, it's used when all values over a finite range are considered to be equally likely. Something that is used sometimes when no other information other than the range is available. Okay, the Weibull and gamma distributions are two distributions that are closely related to the log normal, which we've talked about, as well as the gamma rather. And like the log normal, changing parameter values, shape, shift, and scale can cause the distributions to change shape and become more or less skewed. You can see that from the graphs here. In all these functions, increasing the shape parameter will push the distribution towards the left, okay, towards the left. And in fact, at high values of sigma, the left tail disappears entirely and all the outliers are positive. In other words, we don't have any left-hand distribution on this. Look more like a exponential in that case, at least in that sense. And you'll see that the distributions will start to resemble the exponential, characterized by a location m and scale parameter b, and you can see that from the figure here. So the question again on how of which of these distributions would best fit the data is of course dependent on how severe the asymmetry of the data is. In other words, how uniform is it from left to right? If I pick a mean value, does the left-hand side look like a mirror of the right-hand side? If not, then it's asymmetric. So if you've got moderate positive skewness, where there's both positive and negative outliers, the standard log normal will usually work. As the skewness becomes more severe, you may need to shift to a 3-parameter log normal or a Weibull distribution and modify the shape parameter till it fits the data. And at the extreme, as we talked about, when there becomes no negative outliers, then effectively the exponential function is probably the best pick for that. And again, using the ARENA nomenclature, you've got the Weibull call, and then the beta and alpha parameters are plugged in, the shape parameter and scale parameters. And again, these are positive real values. Our range is only positive, 0 to positive infinity. You can see the mean and the variance is calculated here as well. So again, it's a widely used distribution in reliability models. It's very useful to represent the lifetime of a device. So if you've got a system that consists of large numbers of parts that fail independently, and if the system fails when one single part fails, okay, which are two important characteristics that you need to define up front, then the time between successive failures can be approximated by the Weibull distribution. So things like mean time between failure can be calculated using the Weibull. So you'll see that a lot in life cycle type simulations and calculations. And you can also use it to represent non-negative task times that are skewed to the left as well. But that's the place that, at least from experience, I've seen the Weibull used most, is in lifetime type stuff. It's very useful for that. But again, you need to, like all statistical process work and picking appropriate distributions, you need to make sure that you meet the criteria going in, which is independent failure of the parts. There can't be a dependency between them, and also that a single part causes a system failure. Okay, so as we look at some of this data methodologies of sort of taking a data set, or simulating it, finding a distribution that best fits it, and then utilizing it in a simulation, one of the things we need to look at is characterizing the data. So one of the things we looked at, and we talked about this a little bit earlier too, is how likely are you to see extreme values of the data relative to the middle values? And that's sort of the shape of the curve that we talked about. And this is a key consideration in what distribution to use to describe the data, and that is the likelihood of extreme values of the data relative to the middle value. So in the case of a normal distribution, as we saw, that likelihood is small. And it increases as we move to some other distributions, such as the Cauchy distribution, which I mentioned earlier, same basic shape, but a little fatter around the tails, if you will. And it often may be realistic to use the latter to describe real-world data, because the benefits of a better distribution fit have to be weighed off against the ease which these parameters can be estimated from the normal distribution. So what it comes down to is a balance between calculation efforts and how complicated they become, and the quality of the resultant data is, and that's something that needs to be weighed. And that comes down to, in some cases, dollars in terms of how much do I want to spend to do this simulation, how much time do I want to spend with it, and the value and the robustness of the data set using a simpler distribution. So the end game, it may make sense to stay with that normal distribution. The data is symmetric, and the likelihood of extreme values is not above some certain threshold that you would set. So the same considerations also apply for skewed distributions, although the concern is generally more acute for the skewed side of the distribution. So in other words, with a positively skewed distribution, the question of which distribution to use will depend upon how much more likely these large positive values are than the large negative values, with the fit ranging from the log normal to the exponential, which would be two distributions that we discussed earlier that we would consider for those applications. So in summary, the question of which distribution best fits data cannot be answered without looking at whether the data is discrete or continuous, symmetric or asymmetric, and where the outliers lie. I have a chart here. Let me just zoom in on this if I can for a second. I think you can see this reasonably well. And it's just sort of a flow chart that you would follow down that will lead you to a distribution. And these are all the questions that we talked about up above in terms of, can we estimate outcomes and probabilities? Is the data symmetric or not symmetric? Is the data cluster around a central value? And then my outliers, where are they? These are all the things that you would look at. And it is broken down first off into discrete and continuous, but even on the continuous side, we can utilize the discrete methodologies in simplifying some of these distributions and use a discrete format instead of a continuous. One of the other things we look at, let me zoom back out again here so we can see this a little bit better, is skewness, which we talked about in kurtosis. So one of the things we look at, a fundamental task in statistical analysis, is to characterize the location and the variability of a data set. And one of the characterizations of that is skewness and kurtosis. So skewness is, we talked about quite a bit up above, is a measure of the symmetry or more precisely the lack of symmetry. And that simply means that if you're on the mean and you take the right-hand side and flip it over about the mean or mirror it, it's gonna lay right on top of the left-hand side, so that the data effectively a perfectly normal or Gaussian distribution is going to be symmetric about that mean, left and right. Real data distributions aren't going to follow that typically exactly, but they should in terms of be pretty close. And then the kurtosis is a measure of whether the data are heavy-tailed or light-tailed relative to a normal. So that means that the data sets with high kurtosis have heavy tails or outliers. Outliers are what we're concerned with. Data sets with low kurtosis tend to have light tails or lack of outliers. And a uniform distribution would be the extreme case, right? If we look at the two extremes, normal and uniform would be basically a rectangular curve. So you've got essentially the maximum amount of outliers that you could have, where a normal distribution is going to have light tails, and the outliers are going to be minimal in terms of number compared to the mean. A way to look at this is a histogram, and we had a couple histograms up above as we were characterizing some of the statistical data sets, and that's a very effective way, graphical way of showing skewness and kurtosis. So just for univariate data, y sub 1 through y sub n, formula for skewness is given here, where y is the mean, s is the standard deviation, n is the number of data points, pretty straightforward calculation. In computing the skewness, the s is computed with n in the denominator rather than n minus 1. So that formula for skewness is referred to as the Fisher-Pearson coefficient, and this is something that's used a lot in various statistical software, packages that they can compute rather the adjusted Fisher-Pearson coefficient, which gives an adjustment for sample size as the adjustment approaches 1 as n gets large. So for reference, the adjustment factor is 1.49 for n equals 5, 1.19 for n equals 10, and so on. You can see that as n gets large, that adjustment approaches 1. So for a normal distribution, the skewness is actually 0, right? The data is symmetrical about the mean, and any symmetric data pattern should have a skewness near 0. Negative skewness indicate that the data is skewed left, and positive values for the skewness indicate that data are skewed right, which sort of makes sense. By skewed left, we mean that the left tail is long relative to the right tail. So the negative side is predominant over the right side. Skewed right means that the right tail, again, would be long relative to the left tail. If the data is multimodal, and in fact that there's two humps in it, if you will, then this sign may affect the sign of, this may affect the sign of the skewness. So some measurements that we discussed and some data sets that we discussed up above have a lower bound and are skewed right. Example of that would be reliability studies, because failure times cannot be negative, so it's characteristic of the physical system as well. There are also some other, as you might guess, some alternative definitions of skewness, and we're not going to get into these in any depth, but just be aware that there's other methodologies in addition to the Fisher-Pearson that we talked about above. And different data sets may apply better, may give you a better description of the data set, but sort of beyond where we're going to go with this. So for kurtosis, again, a univariate data, y sub 1, y sub 2 through y sub n. The formula is given here for kurtosis. Y sub bar is the mean, S standard deviation, n is the number of data points. Again, n is in the denominator for standard deviation rather than n minus 1. Kurtosis for a standard normal distribution is 3. And some sources that, because of that, use the following definition of kurtosis, often referred to as excess kurtosis. So with a normal distribution, standard normal distribution, our kurtosis will be 3 or very close to it. And what that allows us to do is sort of corrects that, and then allows us to say that our kurtosis is actually 0 for a standard normal distribution as opposed to 3. And that's why you're subtracting 3 off of this just to get you back to 0, sort of level shift back to 0, if you will. So in addition, with the second definition, positive kurtosis, which would be where 0 is for our normal, would indicate a heavy tail distribution, and a negative kurtosis indicates a light tail distribution. So again, which definition is used, a matter of convention. Useful, the text that I pulled this out of uses the original, but useful to mention that in some way, so that if you see a 3, you know it's a normal, or if you see a 0, you know it's a normal. And just some examples of data sets. These are little histograms that have been drawn with the appropriate skewness and kurtosis levels. As I said, in this case, 3 is considered to be normal. And you can see that here, the normal distribution is 2.96. Our skewness is 0.03. So again, assuming this is a real data set, or random numbers, I guess is what they're generating here. This, approaches 0. This certainly approaches 3. So that's what we're looking at. And in this case, you've got a positive heavy tail on the right, kurtosis 4.46, skewness of a positive skewness, which indicates a heavy tail to the right. Okay, just some other examples you can take a look at here as well. So again, the first is a normal distribution. Again, pretty close to being with as a statistically well-behaved tail. Gives you a skewness of 0.03 and a kurtosis of close to 3 or 2.96, and verifies that symmetry. Second histogram is a double exponential distribution. Double exponential is symmetric. Compared to the normal, it's got a stronger peak, more rapid decay, and heavy tails. And you can sort of see that here as we look at that. So you expect a skewness close to 0, which is what's reflected, and a kurtosis higher than 3, which again is what's reflected here. Skewness in this case 0.06, kurtosis approaching 6 or 5.9. And then the third one is from a Cauchy distribution, which we talked about real briefly, didn't really get into, but in this case, they limited the values from -10 to 10. Again, these are random numbers that we're generating here. The Cauchy, again, is a symmetric distribution, heavy tails at the center, with a single peak at the center of the distribution. And it is symmetric. You would expect a skewness near 0. With heavier tails, you'd expect the kurtosis to be large, or larger rather than a normal distribution, and that's what you would anticipate here. And then the fourth one is a Weibull distribution with a shape parameter 1.5. Again, that's a skewed distribution. Skews depends on the value of the shape parameter. Degree of decay as we move away from the center on the value of the shape parameter, and for this data set, the skewness is 1.08. Kurtosis is 4.46, which you can pretty much makes intuitive sense as you look at the graphs. So again, many classical statistical tests and intervals depend on normality assumptions, which we talked about some, and the significant skewness and kurtosis would indicate that the data is not normal. So if a data set exhibits significant skewness or kurtosis, as indicated by a histogram or some numerical measure, what do we do? So one approach is to apply some transformation to the data to try to make it closer to normal or more nearly normal. One of these is the Box-Cox transformation. It's a useful technique to try to normalize a data set. And the way that's done is you're taking the log or square root of a data set, and it's that methodology is often useful for data that exhibits moderate right skewness. Another approach would be to use techniques based on the distributions other than normal. For example, in reliability studies, the exponential, Weibull, and log normal distributions are typically used as a basis for modeling rather than a normal, again, because it's a better fit to the data. And the probability plot, correlation coefficient plot, and probability plot are also useful tools for that. And again, as I mentioned, the skewness and kurtosis calculations are typically available in most general purpose statistical software programs. So one of the things we want to do as we're looking at data is we want to see how good our fit is, right? We want to test for the fit of our data to our assumed statistical distribution, right? So easy way to do that is to make a histogram and compare that, okay? And that's what we've done here. This is a distribution of price-earnings ratios, so the price of the stock versus the earnings per share that a company achieves for U.S. stocks, and again, this is in early 2007, and then we superimpose the normal distribution upon that, okay? So you can see from this that the fit's not so good, right? We're clearly diverging from the normal distribution, so any assumptions that we've utilized using this, lack of fit, you can see a nice normal curve there. And our mean's over here somewhere, and we've got a huge tail on the right, not so much on the left. Clearly way off of a normal distribution. So that would be a bad fit. If this was if you were going to do a statistical analysis based on this data, and your assumption was that it was normal, and then your calculations were based on that, you would be getting some values that wouldn't match up real well, wouldn't correlate real well to the physical world. So that's the easy way, and that's a real quick way to graph some data. If you can graph, so easily today using Excel or any type of a spreadsheet or whatever, you can easily pop a couple of graphs up and just see how well things look. Another way to do this would be to sort of make a best fit line, if you will, through this histogram. If you wanted to do that and see how well that fit, you could see this really wouldn't fit very well just because of how skewed it is. Another way to do it would be to compute the moments of the actual data distribution. In other words, the mean, the standard deviation, skewness, and kurtosis, and then examine them to fit the distribution. And if we did that in this case, we'd see that life's not so good. In this case, we're looking at normal distribution. A skewness would be 0, not 3. So this is a little misleading, and then we sort of changed this is from a different text is why. In this text, when we were talking about 3 being a good value for kurtosis, that's not the case down here. So that's been corrected. The value we're looking for is 0. We're way off. Even with 3, we'd still be way off, but this just makes it worse. So a skewness of 3, again, it should be 0, and a kurtosis of almost 12, again, it should be 0. So we're not looking so good. So we can easily reject that hypothesis. This, would give you just another sort of peek at the data and its comparisons. The graph sort of tells the story on this stuff. So again, the typical tests for goodness of fit compare the actual distribution function of the data with the cumulative distribution function of the distribution that's being used to characterize the data, to either accept the hypothesis that the chosen distribution fits the data or to reject it. So not surprisingly, given its constant use, there are more tests for normality than for any other distribution. In other words, the normal distribution is utilized in a real large percentage, I don't know what it would be off the top of my head, but a real large percentage of statistical analysis. That Gaussian bell curve normal distribution is really the most widely applied. So again, because of that, you would certainly understand why there's so many tests for it. So one of the ones that's been around for, I guess that's 50 years, is the Kolmogorov-Smirnov test. There's others. Again, we're not going to get into this in any depth. Just understand that there are tests to see if you fit your distribution. And there are also tests to see if you fit the other distributions as well, not just normal, but these are sort of more useful. And if we look at that, we see that we're not very normal. I can zoom in on that a little bit. So you can see statistically does not give us a good value. Any of these tests that we're using does not give us a good fit. And then there's also graphical tests where you make a probability plot to assess the hypothesis that the data is drawn from a normal distribution. And you can see that, again, we don't really fit up very well here. The green being the normal, the red being our actual data set. So again, I keep mentioning this about the normal distribution. It is, in fact, the easiest one to work with, or one of the easiest ones. So one of the first things you probably want to do with a data set is to see if you can use that distribution, how well it plugs in. If it doesn't plug in well, then you need to move on from that. But if you can use it, that's that again is probably the easiest from a statistical manipulation standpoint, probably the easiest one to deal with. So finally, in conclusion, raw data is almost never as well behaved as we would like it to be, and fitting a statistical distribution of the data is part art and part science, and there will be compromises along the way. So the key to good data analysis is maintaining a balance between getting a good distributional fit and preserving an ease of estimation. You never want to pay $5 for a dollar's worth of information, is sort of an old adage. And that's sort of the case here. You need to understand how critical your simulation is, what the risks are, what the dollar values that you're putting at risk are in doing this simulation, and then have a commensurate value of simulation to that. I mean, to take it to an extreme, if I could actually test the actual physical model that I'm trying to do for $100,000, I don't want to spend $1 million on doing statistical simulations. On the other hand, if to simulate whatever it is I'm trying to simulate in the real world or in the physical world, would take $1 million, maybe I do want to spend $100,000 on simulation techniques, because maybe that's a good payback. But that's the point. You don't want to pay more for the data or for the information than it's actually worth to you, and that's the whole point of that right there. So and you may in fact decide to settle for a distribution that less than completely fits the data, especially if you can test that and see how robust your solutions are. If your solutions are very robust, you may be fine with that. It may not be an issue. And again, the overwhelming dependence on normal distribution in practice, it's easy to use, easy to understand, and problem is that a lot of times the data doesn't necessarily fit it that well. And I've seen that in manufacturing applications where it's used in statistical process analysis projects, and you've got data that doesn't necessarily fit normal distribution, but it's used anyway. So so that's it for this lecture, and I think we're right at about